Hello and welcome back to this lecture series on foundations of cyber physical systems. So, I believe we left it off here where we are talking in week 12 about intermittent security reinforcement. So, I believe what we were discussing had been like we were trying to find out that how sparingly we can use the security primitive inside the CPS. So, that I mean we do not have to use it always leading to bandwidth issue, but at the same time it is not also fully insecure and it is like just enough secure. So, that even under attacks which are stealthy the system does not become unstable. So, let us continue from where we left off. So, we are trying to figure out like this is our estimation error when there is no FDI, and when there is this false data injection we kind of wanted to derive a formula which would tell me what is the estimation error under FDI, and in a similar vein what is the residue under no false data injection attack, and what is the residue on the sensors I mean what is the residue when there are FDIs happening on the sensors, and then eventually we want to figure out what is the increment in the error and the residue. That means how much extra error is incurred due to the attack in the as part of state estimation, and how much error is incrementally incurred in the residue due to the attack. So, basically we want to figure out with and without attack what is the how bad is the system response. That means how bad is this error and how bad is the residue calculation. That is what we wanted to figure out. Now, if you remember in this regard we have already derived this kind of expressions that well E k, which is it can be expressed like this. Where W is the process noise, observer gain L, these two will get cancelled out. And this is, as you can see, the error in the k minus 1th step in the state estimation. So, overall we can write this. So, this is like a recurrence equation we are able to obtain on the error with respect to the previous error and the process noise in the previous iteration, and this is a system property L, right, the observer gain, and what is the residue in the current iteration. So, that is your computation of error. Now, this is when there is no FDI happening, right, and similarly if we want to figure out what is the estimation error when there is actually FDI happening. So, let us understand what will happen. Then you have this, then this is also state under attack, then this is also state under attack, control under attack, right, and here similarly you have everything under attack here, right, residue under attack. So, what you will get is similar stuff. So, error under attack will be related to error under attack in the previous iteration, the noise that is there, the noise is kind of the same, right. So, and the residue under the attack. So, then what can we say about this? That is the what is the modified error that I am getting, what is the modification or what is the error really induced into the system due to the attack that is happening on some of the sensors. So, we should be able to mathematically write it like this. So, we are basically subtracting error under attack, I mean from this we are subtracting the original error, right. So, what we will have is this minus the one without attack. So, that will give me this minus this and these things will cancel out, right. The and what I will be left with is here the residue under attack minus the standard residue. So, I can say minus L times delta R k, the increment in the residue due to the attack. So, that is how the increment in residue due to the attack will get related with the increment in the state estimation due to the attack, right. Fine. Let us progress from here and we will also try to come up with a relation for this and then so you can see that what is my end goal. My end goal is to figure out due to the attack what is the what is the component of state estimation error that is getting injected, right. So, this is the component in state estimation error and I have been till now successful in creating a recurrence equation for this component in the state estimation error, but at the same time in this equation I have this delta R k term, right. So, what we need to figure out is that well can I have an expression for this delta R k term using which I can replace it with other system parameters and then I would have a way to compute this extra error that is this. So, my end goal is computing this, but now as I see that I need to find out an expression for this which I can put in here and then I can get a more parameterized system property dependent expression for the extra error that is injected due to the attack. So, let us try to figure that out. This is what we want to know, right. So, the residue under attack would be the measurement under attack subtracted from what I estimate that state to be, right. So, this is the expression for the residue, right, because in the previous state I have estimated x k hat. Using that I can apply it on this and measure what is x k, this is x k minus hat, from this I can get x k hat and then I can do this y a k minus this. So, that is like the error that I have in the residue. So, I am computing based on my previous estimate what would be my current estimate of x and that is x k hat. And then I will multiply it with C for modeling the output equation y equal to C x and that is kind of giving me that well what is my current expected output Now, the output that I measure is this, and by definition we have the output that I measure minus the output that I have expected to be my residue, right. So, this is my expression for residue under attack. Now, we also need to find out this, right, which I already know. It is just the similar expression without the attack. So we see that we have YAK and YK here. Now, let's try to write them in terms of the states. So, if you recall, we had this from our discussion in the previous lecture. This is the measurement noise, this is the attack on the measurement. And we had YK when there is no attack, then we simply have this is again the measurement noise there. So, if you substitute all those values, so with this I can replace YAK minus whatever you already had. This is under attack, of course. Now, similarly, if you replace YK with this equation, so you land up with this kind of an equation, right. As you can see, these terms will get cancelled out here, and you should be able to write something like this. So, you can see also here you have the estimates and the controls all in the k minus 1th step, and here you have x all in the kth step, right. But you are trying to figure out an expression for delta r in the kth step, and typically we do it like we try to obtain a recurrence from parameters in the k minus 1th state. We would like to derive the parameter in the kth state. So, we will try to express these using expressions for the k minus 1th state. So, if you recall, you had these expressions. The process noise, so let us continue like that. So, that is your x k under attack. and the amount of attack in the kth step. So, this is what you can see. Out of this, as you can see that many terms would of course get like cancelled out, right. So, you have all the controls no well yeah sorry. Yes. So, this is my expression. Now, let us observe one thing. What we are doing here is we are trying to figure out the error in the state estimation under the assumption that the attacks are happening on the sensor measurements only, right. So, it is like under false data injection on sensor measurement, what is the additional state estimation error that is being injected into the system, that is what we want to figure out, right. So, in that way, since we are assuming that the attack is happening here only and not on the control. So, although in general we write this in an attack scenario, but in this case since we do not have this actuator attack, we have this, right, and that would really make these terms cancel out. So, what you will end up with is C times A value of x under attack in the k minus 1 step minus the estimated value of x under attack in the k minus 1 step, right. And similarly, you will have this which is C times A, the value of x under no attack and in the k minus 1 step and the estimated value of x under no attack in the k minus 1 step. So, this process noise also gets cancelled out, right, and you have the amount of attack in the kth step. Of course, it is happening only on the sensor cell. So, you have C A, this is error under attack and so this is error under attack and this would give you error under no attack scenario. So, that contributes to C times A, the incremental error that you have in the estimate, the estimation error. This is the estimation error in both cases and the extra estimation error that is added due to the attack. So, that is what you have for the extra amount of residue that is coming due to the attack. So, you can see that here you have a nice looking expression which is relating that well the change in residue due to attack with the change in estimation error due to the attack, where this is the estimation error under no attack and under attack, right. If we go back to our previous expression that we have derived, it was this. The estimation error, the incremental estimation error due to attack in the kth step is related to the incremental estimation error due to attack in the k minus 1th step with the incremental residue using this relation that we derived. And now here you can substitute this value and let us see what we get. So, of course, this will be substituted here and I would get a nice looking expression . So, you have an AK component also. So, minus L AK. So, what we did is, well, we substituted this delta R k with this, right. So, then I would have A C L coming in the first term, A goes common. So, I minus L C, right, and in the second term I would have L A k, right. So, this gives rise to this dynamical equation on the error in the state estimation. Now, the question is, why are we interested in this quantity? Because this is very much related to how much security I can give. So, you see this is telling me that in one step of control, let us say I have a security reinforcement here due to which this value will be 0 here, but then in the next step with HS sampling period here, the maximum possible value that I can get for the extra state estimation error getting injected to the system would be bounded by this value, and then again it would be bounded by again this value, right. So, if I keep on adding this term over multiple iterations, let us say over some window of length f, that means f times h is that on the timeline. So, that tells me that, well, this entire quantity times h or something like that. I mean, of course, I mean not really times h, I mean this is getting into the system and then again the system is evolving and then again another error is coming up like that, right. So, that much error is getting accumulated into the system due to the attack, right. So, if we now push back this constraint into the dynamical equation, we can actually compute that, well, how much is the extra state estimation error that is getting into the system, and I can compute this as a function of the number of iterations of the system, because this is the amount of error that is getting injected extra in one iteration. So, I will add this up, then again evolve the system to the next step, then again I will add this much up, right, with changes in k to k plus 1 to k plus 2 like that, and I can compute that in each iteration how much is getting added up, right. In that way, as long as this total error plus the current state will I mean also the corresponding residue, and also in the process there is another constant, that is in every step this residue value must be less than the threshold, right. This residue value plus the RAK that also must be less than the threshold, right. So, under these constraints, the amount of error that is getting added up in the system will be measurable once I have this expression that we have created, right. So, I can use this expression to create a rich set. If you remember from our earlier examples that I can really compute a rich set of an automaton. Similarly, if I now create a model of the dynamical system here, and I can create what is the reachable region of the state estimation error under the attack, which is like this rich set, and it tells me that well, as long as my residue is inside some inside inside the threshold, and the increment in the residue is inside a constant, and in my previous iteration I knew what is my state estimation error, I can compute that well what is the extra state estimation error in the current computation, right. So, based on this I can actually see that well what is the reachable region in the system under attack with respect to the state estimation error. Okay. So, as long as these regions flow is within my detector threshold, maybe I am okay, and as long as this reachable region does not lead to any violation of the safety trajectories of the system, the safety boundaries of the system, I would be okay, right. And as you can see that if I increase the value of this horizon length up to which I am not giving any kind of security enforcement, as long as I am increasing that horizon length, what is happening is this error value is increasing, right. So, then this region inside which I have this all the possible state estimation error values, this region size will also increase, right, and eventually it may cross those safety boundaries, which I do not want to happen, right. So, even if I choose let us say a starting point, I know the initial point from which the system starts, and I know that well what is the maximum amount of attack that can happen on each of the iterations. I can figure out during the using these expressions that what is the extra error getting into the system's state estimation, and from that extra error I can compute, I can get an idea that well what is the actual state going to be in which regions in the state space, right. And then from there I can actually figure out that well I am still inside the safe region or not. So, with this we can go further here. So, what we can do is we can create a security policy where the policy states that well the policy is parameterized in terms of these three parameters mu, f and L. Mu is nothing but those positions in the timeline where I am going to apply the security the security primitive, maybe a crypto primitive or some detection primitive, something like that. Okay. So, that is a sequence of those TK values where I apply the security primitive, and then L is basically telling me that what is the maximum separation, this is supremum between these two consecutive values, the differences, all the consecutive time points they are differences, they are supremum. So, that means between any two successive security policy application points you take this and this, you take this and this. So, what all I am trying to say that these need not be equidistant, some of them can be nearby, some of them can be larger, but their maximum separation is given by L, and F is telling me that well after I apply this security policy up to how much time I have this security policy in place. Okay. That means say I apply it at Tk, right, and then I have again this thing at Tk plus 1, and then maybe again at Tk plus f minus 1. That means for f length in the trajectory I have this security policy in place, and then again I will start here, and this separation is given by L. Okay. So, inside an L length I am applying the security policy for f length. Okay. As I am repeating again, this L can change to some L1 here, but they have a max which is bounded, and that is this L value. So, you can also simplify this. Let us say I am creating a security policy which is simply saying 1, 3. So, I mean let us not write mu because it is just a collection of those time points. Let us just say that it is 3, we are not writing the mu here, we are just writing is keeping it unspecified. We are writing 3 here and we are saying 10 here. That means we are simply saying that well let me apply the security primitive in 3 consecutive positions in a 10 length window. That means after these 3 consecutive positions I keep 7 positions where I keep no security primitive, then again I just repeat it. Okay. That means my mu value is nothing but it has a 0 offset, plus 10 times of h. That means these are the starting times where I start giving the security primitive, and I give it for 3 consecutive iterations, and I then don't give it for 7 iterations, and then again I just repeat. So this is a simplistic way. Here I am assuming that the L, the separation is all same for all those windows, but it need not be same in general. So again, just to summarize, this policy is applied as at a minimum f consecutive samples, and the start of each block of f samples will be at most be L times separate, I mean L time steps apart. So like this is the L time step and this is the L time step. Here I have f consecutive places where it is being applied and then it is left. So this is like 3 in our example, the rest is 7, so that L equal to 10, assuming the time steps are all same. So the supremum is equal to all the values. The supremum value is same as all the separation values everywhere. So this part of the treatment has been taken from this paper here. Okay. So when do I say that the system is not perfectly attackable? So suppose I have an LTI system where we have this kind of an integrity policy, and f can be created, f can be related with the number of eigenvalues of the system, and accordingly we can actually create a condition based on which we can deduce that whether the system is perfectly attackable or not. But let us not get into that detail. This is just a theorem we wanted to show you. We are not interested in the details of the theorem for the part of the course. All we are interested in is to understand well how I can compute the extra error that gets into the system due to the attack, and well, once I have a handle on the extra error, how to compute that well with the attack building up over certain iterations, how I can characterize the reachable region, and once I am able to characterize this reachable region, well, how I can select a security policy. So let us say here I have an example that we are trying to show that this is the estimation error, that means the entire error, that is E A K, right. We are plotting it as a function of k here. So this is one point where the security primitive is starting, and it is continuing for this Ti plus f amount of time, okay. And then there is from here to here there is no position where there is any security primitive applied. This is a safety boundary, and the system state estimation error is hovering like this. It could have been something like this, it could have been something like this, etc. But what is important is like this, that here it must decrease. I have a guarantee that this estimation error will decrease here, because I am not allowing any attack here due to the security primitive. Similarly, here I have a guarantee that it will decrease, because again I am applying the security primitive here and I am making it go below this point. Okay. The question is how much low I want to make it. I must apply the security primitive up to that number of iterations, so that this unnecessary error that is getting into the system as part of the attack but not part of the system noise is reduced that much, such that again when I leave the security primitive and let the attack continue, note that the attack is also not unbounded, it is bounded by a small value, because beyond that it will be detected. Attacks are stealthy here. So I want to reduce it up to that point, such that after this if I leave it on its own and the attacks can happen, it won't rise beyond this safety boundary, it will be inside this. So suppose for this I see that it goes beyond, that means I must secure it for a longer amount of time, so that it should come down somewhere here, so that then if I leave it, it is unable to go beyond. Okay. So that is the point. This curve could have been anything here. I don't have any control on that because of the stealthy attacks, but I have a control from this point to this point, when I decide that well what should be the length of this interval, so that inside this interval I bring down this error to such a point, such that from where if it again rises inside the next interval starting point, when again the security primitive will come and attacks will be limited, but inside this small window it won't be able to make the system veer outside this safety bound. So that is the point we are kind of trying to make here. So these authors in this paper, they actually applied this on some trajectory tracking controllers, and as you can see that what they are doing is they are changing the mu value. So, let us understand what the mu value means. It is basically those time steps, right, when the security policy will apply. So, they are applying it with a period of 20, with a period of 30, with a period of 35. That means, at the lower for this you are applying it more frequently. You are applying it once every 20 cycles, once every 30 cycles, once every 35 cycles. When you apply it here, your F value is 1, L value is 20, 30 and 35, and accordingly mu is just 20 times h, those time points, right. Mu basically is the time points when the policy is applied. So, mu is 20 times h, 30 times h, 35 times h, L is equal to 20, equal to 30, equal to 35, and F is equal to 1 in all these cases, right. So, when you run it, you can see that here the policy is less sporadic. So, the error is less, the maximum error is like this. In this case, you apply it after every 30 iterations. So, you let the error build up, but if you apply it after every 35 iterations, you make the error build up to a larger value, and due to that what is happening is it is crossing this safety boundary. Okay. So, this is my safety boundary and it is crossing it. So, I will like to not select the security policy to be applied every 35 units, but I would really like to have it at 30 or better say at 20 if the system bandwidth allows it to. Similarly, you also have an example by these authors from their work on the example of a degraded cooperative adaptive cruise control. So, this was a trajectory tracking system, and here you have a cooperative adaptive cruise control. That means, you have multiple vehicles and they are following as minimum separation, and they are trying to drive them together. So, this is the system matrix for such a system. In our tutorials, we will actually show you that well how to build these system matrices for such a platoon, how to build the system matrices for the trajectory tracking system, etc. Here we are just starting from the system matrices for the sake of time here, and we are trying to show you that well how these estimation errors change, and in this case we are showing you that how this error is going up, but the choice of security policy here has been such that well we are able to keep it below this safety threshold. This is the safety threshold here. So, we enforce an integrity on f equal to 2. So, here you see, here we are saying that the security policy is such that you enforce the policy once in every 20 iterations, but when you enforce it for 2 cycles. I mean twice you give the security policy. Okay. And so, that means if I give it just once inside 20, then maybe I am not able to bring down the curve on the estimation error so much, right. But if I give it twice inside a 20 number of iterations, then it stays just below this safety line. Okay. So, that is about it here, and also we will like to talk about something else. So, if you remember, we earlier did a derivation on on residue calculation. So, here we had been talking about this covariance of residue, and we actually tried to give you a proof, right, that well how for this estimation for this residue how we can calculate this covariance of residue, and we showed that well why this should be equal to this, but I guess after that we directly wrote this thing. So, maybe I would just like to explain a bit on that. So, let us remember what was our expression for residue itself. Where all these symbols you understand they have the usual meaning, right. This is the error, set estimation error, and Vk is your measurement noise, right. Now, note that this measurement noise and also the error, because we earlier discussed the error is following a Gaussian here, right. So, what will happen is if you take an expectation over this RK or RKS transpose just by themselves, you are taking an estimation of the mean, you are taking an estimation of this error which is positive or negative with a 0 mean and distributed in a Gaussian manner, and Vk is also an identically independently distributed Gaussian with a 0 mean, right. So, what will happen is expectation of both these will be C times expectation of this, which would be 0, C times and plus the expectation of this, which would be 0, right. Then what remains is expectation of RK transpose, right. So, if you just try to compute that, let us see how that happens. So, here you have RK transpose, that means this is a transpose over this, that would mean EK transpose times C transpose. So, that is so, now if you carry this expectation inside, you will get this from the first term. K transpose, and you will have expectation of EK VK and expectation of VK EK like that, EK transpose like that. Now, so that means I mean these will be the terms that will be 0, and the question is why they are 0. Of course, because we will be assuming that EK and VK are independent. So, whenever you will have terms like E of EK and VK, which you will get here and here, right. You can write them as E of this and E of this, and here this will become 0, right. So, that is why this is with 0, and you have essentially then C times covariance of the state estimation error, which would be given by this sigma E and C transpose then, and then you have the covariance of the process noise, right. So, for the same variable, so that is a variance of the process noise. So, that is sigma V, which is a parameter of the Gaussian distribution. So, you will be assuming that V k is distributed following a Gaussian with 0 mean and variance sigma V. So, this is essentially sigma V, and similarly and this is the variance of the error. So, let that be sigma E. So, in this case what really happens is when you measure the residue, well, you take it, right, and then you generate the chi-square stat using this expression, which is a property of chi-square stat, and here you are using sigma r, which is nothing but the variance of the residue. So, essentially you are measuring R k under attack, and you are weighting it with the variance of the residue or basically the variance of the variable R k, right, and you calculate the variance using this expression, and you apply this assumption that E k and V k are independent, because anyway there is a good assumption, because E k is a property of the system and V k is a property of the environment, right. So, based on that you can come to this expression, and from here you just apply you just replace this with the variance of error. We are assuming that this is known to you, and the variance of the noise, which you also consider as a known parameter as part of our noise model, right. So, given that we know that the variance of error and variance of noise, we can write what is the covariance of residue, and then you use the covariance of residue right here. Okay. So, I believe this explanation was missing, but now we have it there. So, that is pretty much about our discussion on techniques for attack detection, techniques for attack mitigation. Some of these are at a bit advanced level. We are trying to give you a basic idea that why these are important and how some of these techniques can be applied. Some examples on this we will try to cover in the tutorials that we have as part of the weekly tutorials that we will have in the course, and I hope with that you will have a fair idea about how system properties can be used to secure CPS systems. Okay. With that we will end our lecture. Thanks for your attention.